In the year 1928, a young man uttered a statement that nearly drove Heisenberg to distraction. He asserted that within the universe, there exist particles possessing negative energy. Upon hearing this, Pauli immediately declared his intention to abandon quantum physics in favor of writing novels. Heisenberg's response was even more vehement. In a letter dispatched to Bohr, he wrote, "I find the present situation utterly absurd. I have come perilously close to despair, to the point of considering a change of field." Yet, what proved even more alarming was that, 4 years later, this seemingly outlandish prediction was vindicated. At the California Institute of Technology, Anderson captured an unusual trajectory within a cloud chamber. It resembled an electron, yet it bore the opposite charge. This marked humanity's inaugural encounter with antimatter. And this revelation implied that, at the universe's inception, for every billion particles, merely one endured, while the remainder were annihilated. The very existence of you and me constitutes a miracle on the scale of 1 in a billion. So, who was this young man who threw the entire physics community into disarray? His name was Paul Dirac, a 26-year-old British physicist. Born in 1902 in the city of Bristol in England, Dirac grew up in a household where his father, a stern French language teacher, compelled him to converse in French at home, rendering the young Dirac reticent and withdrawn from an early age. His childhood was far from idyllic, marked by silent meals and relentless academic pressure, forging a man later described as a quiet individual, almost devoid of emotional expression, yet endowed with an intellect so razor-sharp that it could pierce the profoundest enigmas of the cosmos. He studied electrical engineering at the University of Bristol, where he felt as though he were wandering through a labyrinthine forest of technical complexities, amid humming machinery and tangled wires, though his heart yearned for the purity of mathematics. Subsequently, he transferred to the University of Cambridge, where the vibrant academic atmosphere, alive with murmured debates in ancient lecture halls, nurtured his burgeoning talent. At that time, he stood upon a podium in Germany, delivering lectures in a manner most peculiar. The physicist Eugene Wiener remarked that his teaching style resembled the recitation of a technical manual, utterly bereft of emotion. His voice droned steadily, akin to a gentle breeze riffling through the aged pages of a library tome, devoid of smiles, bereft of emphatic gestures, offering only numbers and equations flowing forth with a precision that bordered on the chilling. Yet this seemingly awkward young man advanced a theory that none of the physics luminaries could countenance. What occupied Dirac's inquiries? He sought to unify Einstein's theory of relativity with quantum physics. The 1920s represented a tumultuous, yet exhilarating era in physics, as the classical world of Newton crumbled beneath the weight of novel discoveries. Heisenberg's uncertainty principle compelled a reconsideration of precise measurements, as if the universe were engaging in a perpetual game of hide-and-seek with humanity, refusing to divulge both position and velocity simultaneously. Schrödinger's wave equation depicted particles as ripples propagating through space, much like the echoing resonance of a musical note in a vast chamber. And Einstein, with his special theory of relativity in 1905, transformed our perception of time and space, as though stretching the very threads of reality. In 1905, Einstein unveiled his renowned formula: energy equals mass multiplied by the square of the speed of light. This equation informs us that mass and energy are interchangeable. Envision, if you will, a tranquil morning in Bern, Switzerland, where Einstein sat at his desk, amid the ticking of a clock and the faint aroma of coffee, inscribing that formula which would unlock the gateway to nuclear energy in later years. However, a complication arose. When one extracts the square root of this formula, two solutions emerge, one for positive energy, another for negative. In classical physics, negative energy is entirely non-existent. Thus, it was universally dismissed. But Dirac demurred. He discerned that upon merging relativity and quantum physics, the negative energy solution proved inescapable. In the quantum realm, particles may traverse as waves, manifesting in multiple locales concurrently. They defy conventional rules. Should negative energy particles truly exist, what might ensue? An electron could emit infinite energy, plummeting into ever lower negative energy states, ultimately dragging the entire universe into oblivion. This was why Heisenberg deemed it the most dismal chapter in modern physics. Picture Heisenberg, with his disheveled hair and weary eyes after sleepless nights of contemplation, penning his missive to Bo in a dimly lit room in Copenhagen, where the sea's waves lapped at the window like the universe's whispered secrets, feeling as though he teetered on the brink of an abyss without end. For the theory was logically impeccable, yet practically catastrophic. Pauli could scarcely endure it. He genuinely composed a letter announcing his renunciation of quantum physics in pursuit of composing utopian novels. Imagine those perched atop humanity's intellectual pinnacle, compelled by a 26-year-old to contemplate career shifts. Such was the depth of their despair. Pauli, with his forthright demeanor and laughter echoing through conferences, suddenly found the physics world alien, as if lost in a shadowy forest devoid of egress. Yet Dirac persisted. In 1928, he derived a novel equation, subsequently known as the Dirac equation. This equation seamlessly amalgamated relativity and quantum mechanics. It could forecast the behavior of particles moving at high velocities with exquisite accuracy. The Dirac equation transcends a mere string of arid mathematical symbols. It is a masterpiece, portraying the electron as an entity with spin, akin to a diminutive sphere whirling furiously, and predicting its magnetic moment with astonishing precision. For instance, why does gold exhibit a yellow hue? Because the gold nucleus harbors 79 protons. Its electrons are drawn inward with such force that their velocities approach the speed of light. The conventional Schrödinger equation fails to compute this accurately, but the Dirac equation succeeds. Contemplate gold, gleaming under sunlight, its color not merely aesthetic, but the outcome of electrons hurtling at near-luminal speeds, yielding a distinctive light absorption. Why does mercury remain liquid at room temperature? For analogous reasons, the Dirac equation furnishes the precise explanation. Mercury, with its shimmering droplets rolling across a surface, resists solidification like other metals, because its electrons move so swiftly, altering chemical bonds. Nonetheless, this equation yielded a byproduct. It foretold a hitherto unseen particle. This entity mirrored the electron in mass, but bore the inverse charge. Dirac termed it the anti-electron. At the time, none believed in its tangible existence. It was regarded as mere mathematical whimsy. The turning point arrived in 1932. At the California Institute of Technology, a graduate student named Carl Anderson toiled. Born in 1905 in New York, with Swedish immigrant parents, Anderson matured amid the bustling city's cacophony of ship horns and neon lights, yet he chose the serene path of science at the California Institute of Technology. His endeavor involved studying cosmic rays. What are cosmic rays? They comprise high-energy particle streams bombarding Earth from space. They incessantly assail our atmosphere, like invisible showers from distant stars, bearing the cosmos's secrets. Anderson employed a device known as a cloud chamber to observe these particles. The cloud chamber brims with saturated vapor. As charged particles pass through, they leave white trails, reminiscent of aircraft contrails etched across the sky. One day, Anderson discerned an anomalous trail in a photograph. This path curved oppositely to an electron's in a magnetic field, akin to a positively charged electron. Initially, Anderson surmised it was a proton, given proton's positive charge. But that proved erroneous. A proton's mass exceeds an electron's by 1,836 times. It could not traverse such distances through air. The trail indicated a lightweight particle, nearly as light as an electron. Anderson stared at this image for an extended period, perhaps in a dimly lit laboratory amid the hum of machinery, his heart quickening as he grasped something extraordinary. He realized he might have uncovered an entirely novel particle. He christened it the anti-electron, or positron. He even attempted to rename the electron as the negatron. But that moniker failed to gain traction. In September 1932, Anderson published this discovery in a scientific journal. The world was astounded. Did you know? When Anderson detected the positron, he was utterly unaware of Dirac's prophecy. He was an experimental physicist, immersed in laboratory work, oblivious to the latest theoretical advances, as if mining gold without a pre-drawn map. And what of Dirac? He had prophesied the positron's existence in 1928. Yet even he harbored doubts. Upon the publication of Anderson's paper, Dirac likely pondered inwardly, "Good heavens, could my casual calculations have been correct?" This stands as one of science's most serendipitous discoveries. Anderson did not seek to verify Dirac's theory. He merely observed cosmic rays. The outcome collided with antimatter. In 1936, Anderson received the Nobel Prize in Physics for discovering the positron. He was 31 years old, becoming one of the youngest recipients of the Nobel Prize in Physics in history. Yet the conundrum persisted. The specter of negative energy particles lingered. If positrons could descend into negative energy states, the universe would have long since perished. Dirac proffered an even more audacious theory, the Dirac sea. He posited that the vacuum is not empty but an infinite deep ocean, teeming with negative energy electrons. These negative energy states are fully occupied, akin to a cinema packed to capacity. No vacancies exist. Thus, ordinary positive energy electrons cannot descend. They remain dutifully in positive energy states. What, then, is a positron? Dirac explained that a positron is a vacancy in this ocean. When a negative energy electron is excited outward, it leaves a void in the sea. This void manifests as a positively charged particle, namely the positron. When a positron encounters an electron, the electron falls back into the sea, filling the void. Both vanish simultaneously, releasing energy. This process is termed annihilation. Can you envision it? The vacuum beneath our feet is, in truth, an invisible ocean of electrons. We resemble bubbles adrift upon this sea's surface, with gentle yet ceaseless waves lapping in the silent void. This theory sounds preposterous, yet it is mathematically sound. At the time, many leading physicists deemed it excessively fanciful, yet they could identify no flaws. Later, in 1941, the Swiss physicist Stueckelberg offered a more elegant interpretation. He suggested that negative energy particles travel backward in time, equivalent to positive energy antiparticles advancing forward. It evokes science fiction, yet it holds mathematically, as if time bends in peculiar arcs, forming loops in the universe's flow. A few years hence, the eminent physicist Richard Feynman illustrated this concept in his celebrated Feynman diagrams to depict particle interactions. In Feynman diagrams, antiparticles are particles journeying backward through time. By the 1970s, every particle possessed a corresponding antiparticle. The electron has the positron, the proton the antiproton, the neutron the antineutron. They share identical masses, but opposite charges. When a particle and its antiparticle meet, they annihilate, converting their entire mass into pure energy, for the formula energy equals mass multiplied by the square of the speed of light. This engenders a cosmic enigma. Why is our universe composed of matter rather than antimatter? Presumably, the Big Bang produced equal quantities of matter and antimatter. If so, they would have annihilated entirely, leaving a universe of mere photons. No galaxies, no stars, no us. Yet we persist. This indicates that, at the universe's nascent moment, matter slightly exceeded antimatter. Scientists have calculated that, for every billion pairs of matter and antimatter particles, there was one extra matter particle. That surplus matter particle survived the annihilative fray. It formed the entirety of today's cosmic matter. You, I, Earth, the Sun, the galaxy, all stem from that 1 in a billion asymmetry. Whence this asymmetry? It remains one of modern physics' grandest unsolved mysteries. Scientists have proposed numerous theories, such as CP symmetry violation, leptogenesis mechanisms, and more recently, in 2025, experiments at CERN have yielded fresh clues. For instance, the LHCb experiment has observed asymmetry between matter and antimatter in baryon particles, marking the first detection of charge parity symmetry breaking in baryon decays, a pivotal step toward understanding why matter predominates, as though the universe reveals a subtle bias, a minuscule imbalance sufficient to preserve all existence. This discovery, stemming from meticulous analysis of particle collisions, suggests that the mechanisms underlying this asymmetry may involve novel physics beyond the standard model, with implications for baryogenesis, the process by which the baryon asymmetry arose in the early universe. Furthermore, the ALPHA experiment at CERN has achieved a monumental advance in producing and accumulating antihydrogen, generating over 15,000 antihydrogen atoms in mere hours through an innovative positron cooling technique involving laser-cooled beryllium ions for sympathetic cooling, enabling more precise comparisons between hydrogen and antihydrogen to probe fundamental symmetries. This breakthrough, reported in late 2025, accelerates antimatter studies dramatically, allowing scientists to scrutinize these atoms with unprecedented detail, as if cradling fragments of a vast cosmic puzzle in their hands. The BASE experiment has likewise advanced measurements of antiprotons, employing penning traps to confine them and achieving the first coherent spin spectroscopy on a single antiproton, yielding ever more accurate assessments of their magnetic moments and revealing minute differences that might elucidate matter's dominance. These findings invigorate researchers, as though they stand upon the shore of a new ocean of knowledge, with the rhythmic surge of data from the Large Hadron Collider echoing like distant waves. In 2024, the Large Hadron Collider at the European Organization for Nuclear Research, CERN, commenced a series of novel experiments. They endeavor to unearth the origins of the matter-antimatter asymmetry. They have even constructed a dedicated antimatter trap, utilizing magnetic fields to suspend antihydrogen atoms, scrutinizing their properties, akin to caressing phantoms from a mirror realm. Antimatter transcends theory. It finds practical application in our daily lives. Positron emission tomography scanners in hospitals harness antimatter. Physicians administer to patients a tracer substance containing radioactive isotopes. These isotopes emit positrons. Upon encountering electrons in the body, positrons annihilate, producing two oppositely directed gamma-ray beams. Detectors capture these rays, enabling the reconstruction of three-dimensional images of the body's interior, aiding diagnoses of cancer, heart disease, and other ailments. Imagine a serene clinic room, with the software of the scanner, and subdued lighting, where positrons annually aid in saving millions of lives, transforming antimatter from an abstract notion into an indispensable medical tool. Moreover, scientists explore antiproton's potential in cancer therapy, where they might target diseased cells with greater precision, minimizing harm to healthy tissue, like an arrow piercing the darkness with unerring aim. Even in the future, antimatter could propel spacecraft engines, unleashing colossal energy to ferry humanity to distant stars, amid the engine's roar and the exhilarating sensation of departing Earth. In 1933, Dirac received the Nobel Prize in Physics for discovering a new productive form of atomic theory. He shared this honor with Schrödinger. That year, Dirac was 31. Yet upon receiving the award, he remained composed, as in all his pursuits. He exhibited scarcely any emotional fluctuation, uttering merely a thank you, as if the prize were but a minor note in his life's symphony. Dirac's personal life brimmed with drama. In 1934, his friend Eugene Wiener introduced his sister, Margit, to him. These two were nigh on a pair of antiparticles. Dirac possessed scant empathy, silent and taciturn, like a stoic rock amid a flowing river. Margit was effusive, loquacious, resembling a babbling brook without cease. Dirac recognized his own deficiency in emotional expression. Yet this marriage proved oddly felicitous. It endured until Dirac's passing in 1984. A mutual acquaintance uttered a classic line: he granted her status, and she bestowed upon him life. Thus, one might say that in the universe, particle-antiparticle pairs exist. Upon meeting, they annihilate one another. But there also exist human pairs akin to antimatter. Upon encountering each other, they forge perfect equilibrium, like interlocking puzzle pieces in life's tapestry, yielding warmth and serenity amid science's tempests. Returning to that pivotal moment in 1932, when Anderson captured that photograph, he could scarcely have imagined that this seemingly ordinary white streak would reshape humanity's cosmic conception. The discovery of antimatter not only corroborated Dirac's wild prophecy, but also flung open a portal to novel worlds. It reveals a universe far more symmetric and intricate than envisaged, yet more enigmatic still. Today, scientists continue to pose questions. Whence that 1 in a billion asymmetry? Might antimatter galaxies lurk in the universe's depths? Could we harness antimatter for ultimate energy sources? Answers to these queries may surface one future day, akin to Anderson's moment in his laboratory of yore. And all this originates from that bashful young man in 1928, who uttered those words upon a German podium, a man who altered our comprehension of our own existence within this vast universe.